Okay, hi. So in this first video, we're going to be talking about what a histogram is and how we can create a histogram and some of the different shapes that we have here. So first off, you can kind of see our definition is that a histogram is a graph that's going to organize quantitative data into ranges created by the researcher that helps us see the overall shape of the distribution. So we've already talked about density curves, which is another way to see the overall shape of the distribution. And oftentimes we'll actually see them overlaid on top of each other, the density curve on top of the histogram, because they are kind of related with this idea of the overall shape and where the data is. So here we have an example of a histogram. And notice that your first thought might be like, oh, that's a bar graph. So there are some differences between a histogram and a bar graph, sorry. The first one here is that our bars actually are going to touch each other. If your bars are touching, then you know that it is a histogram versus if there's space between them, they're bar graphs. Also, for bar graphs, instead of having from 0 to 5, from 5 to 10, from 10 to 15, a range or an interval of numbers, you would just have a category. So maybe these would be, if we could do grades, you might just say A, B, C, D, or F. They would just be specific categories. But for a histogram, it is an interval of numbers. And because it is an interval of numbers, it is continuous. As soon as 5 is done, it's every number between 5 and 10. As soon as 10 is done, it's every number between 10 and 15. And so they touch because there is no space between these intervals. Every single number is going to fall directly into one of our intervals. So we are going to clump our data, which you kind of do with categorical or qualitative data, and you would use for a bar graph, but our clumps are going to be called classes. Sometimes I've seen them called bins, and they are just going to be intervals of numbers. So one of the things that go along with this is it's really, really important that we notice that our data points can't fall into two of these classes or bins. So we have to make sure that when we are creating these classes, we're making sure it's impossible for a number to fall into two of them. So what I mean by that, if we look at the example here, 5 is our border number. Well, the first class is 0 to less than 5. So any number that's between 0 all the way up to 5 would end up in this one. But as soon as we hit the number 5, it belongs in the next class. So notice 5 is kind of on both sides of it, and we make it very obvious with the less than sign that if it's actually 5, it's going to fall into this category. Same thing with 10, it's going to fall into the next one, 15, 20, 25, and 30. And so we're really showing that each specific number, there's no possible way it could fall into two different classes, and also that our classes are continuous. As soon as a number ends in this one, it must fall into this one. So some things are the overall shape of this. Once again, it's always going to kind of be on the x-axis and the y-axis. They're going to have two different things here. Your actual kind of like data goes on the x-axis. And what I mean by that is the numbers have to deal with what you're actually trying to find. So this table is presenting the percent of residents from each state that were born outside of the US. So down here, because for each state we are getting their percent, then down here we have percents, and our percents go from 0 to 30. If we had a higher percent, we know the percents could go all the way to 100, then our x-axis would go from 0 to 100. So it's actually what the data is, what percent of it, what data did you collect goes here. Your y-axis is your frequency. It's the number of answers that fall in this interval. So I don't have all of the data that was used to create this histogram, but what this is saying is that 20 states had 0 to 5% of people born outside of the US. There was one state that had 25 to 30% of their residents born outside of the US. And so this is how they created this histogram. The first thing you're always going to see is this frequency table, which is just putting your data, you're defining your classes, and then you're actually stating how many of your data points fall into each of those classes. Then we go ahead and we put on our histogram. So we go from our classes, so 0 to 5, 5 to 10, 10 to 15, 15 to 20, 20 to 25, 25 to 30. And then once again, how tall it is based on this number. So we can see that 0 to 5 goes all the way up to 20, 5 to 10 goes to 13, and etc. So this is where on the x-axis you end up, and your count is how tall you end up. So where on the y-axis is each bar going to go to? So that's what a histogram is and how we create one. Histograms, like I said, are really interesting to help see the overall shape. If I were to draw a density curve over this one, notice it would peak up to hit this, and then it kind of skews its tails down like that. So this is what our density curve beneath it might look like. For those of you guys who've watched the video on normal curves, we can see that this one is not normal because it is not symmetrical. I'm going to skip over this part right here to kind of go down here and talk about these different shapes that we could see. And this has to do, once again, with the density curve, but notice that I found that density curve simply by drawing the overall shape of my histogram. So I went up to that top bar, and then I kind of went down to hit all of the other ones. Each bar goes approximately up to it. Some of them have some space on the other side. That's okay, especially as you go on in your mathematical career and you guys start taking calculus. You'll see that this happens a lot when we're still finding the area underneath the curve. So let's talk about these shapes really quickly. The first one I'm going to hit is obviously the normal one, which is symmetric. So we said that this type of graph is a normal density curve. That is because it is symmetrical and the peak is in the middle. So this is the same shape on both sides. And also notice that our different measures of centerness, so our mean, our median, and our mode, are all going to be the same number if it's perfectly symmetrical. Some data is actually normal, and some data, the more you collect it, the more likely it's going to be this way. But not all data is going to follow this pattern. This one had what's called a tail out to the right. So it went up, and then as we went to higher numbers, it skewed off. That would be this shape right here. This one is known as it's being skewed to the right. And so we always talk about the skewed being where is the tail? Where is this bit that's kind of trailing off? And so anything that is skewed to the right is going to pull towards those larger values. So you're going to have the majority of your data here in your lower values, but as you get into those higher ones, you're going to keep getting one or two more into the next class. Notice here, if your data is skewed to the right, your mean is going to be a larger number than your median. And remember, the median is actually, if you were to list out all of your data, what number falls in the middle, versus your mean is taking the average of your data. So they're very interesting, and oftentimes they are similar, but if your data is really skewed to the right, so you've this little trail, you have a handful of your data points falling in these higher ones, where the most of your data is in the lower, then your mean is going to be a higher number, but your median is going to be a lower number. I like to think about your median kind of telling you where most data falls. And we know the mode is what data point shows up the most. So that's always going to be your peak because it's what's showing up the most. The other side of what we can have here is skewed to the left. So for this one, notice that my tail goes out to the left. These would represent my lower numbers because we're on the x-axis. We start with lower numbers to higher numbers. So for this example, most of my data is clumped in my higher numbers, but I still have some numbers that are skewed down here. When I see something like this, I often think about grades on a test. This might be maybe an 80. And so we're saying most people got an 80, and then that's kind of our highest point here. And if we think about it, we know that grades go from 0 to 100. So it makes sense if this is an 80, then maybe from here to here would be 70 to 100. If we think about grades, most grades are going to fall in this range. So it makes sense for most of my data to be here. But we're missing the 0 to 69 realm. And we know that students can score in this realm. That's what these represent, is a handful of people who fall in this huge range. That's why we have this skew. This is only 30 possible grades versus this is 69 possible grades. So that's why it kind of lengthens out, because there's more possibilities for students to get down here, even though the majority of students are going to fall here. The opposite is true here when you talk about the mean and the median. If you have data that looks like this, your mean is going to be lower than your median. Once again, the median tells you where most of your students are, or most of the data is. And so this might be that my median was a 78, but my mean was a 72. If I see something like this, that means the majority of my data is clumped over here in this higher range. The majority, or at least I know exactly half of my students made above a 78. It also means half of my students made below a 78. This mean is that average, and because it's significantly, or maybe not significantly, but because it is lower, then I know that I have this little tail thing that's going on here. So these are histograms. So once again, the histogram is actually the bar graph where you find your classes based on your data, and then you figure out how much fits into each of those classes. Once you have a histogram, you can kind of sketch your own density curve over it. And then once you've done that, you can determine, well, does my data look skewed to the left? So the tail's out to the lower numbers, the peak's out to the right. Is it symmetric? Or is it skewed to the right? Do I have a tail out to the right, but most of my data is to the left? And also remember, we have talked about really briefly that you can also have ones that are bimodal, which have two peaks. They might look something like that. This data is always very interesting, and once again, most often you'll see this as called bimodal because there are two peaks, but there's other ones that could fall like this as well. These are the ones that we will see most often in this introductory statistics level.